All right, so welcome to the final session of Electronics 2, and today we have the presentations for the term projects. Remember that is about 10 minutes, maybe a little bit more, but about 10 minutes per team. And we have 7 or 8 teams that are going to present. I think that it would be best if at any time anybody has questions, just type something in the chat box and I will moderate that and ask the presenters to address the question at an appropriate time during the presentation. So before we start, I guess as a manner of concluding remarks for the course, I wanted to let you know that it was a wonderful experience for me to teach the course for the first time, that I hope that when I have a lot of ideas to make it better and maybe a little bit more challenging for next year. And I wanted to remind you that at the beginning of the course, I told you that there are only but a few courses that have a summative property of bringing a lot of things together, and that course really, it really teaches you a lot. And I hope that you found this course to be that way. I told you that it was going to be that way, or at least that was my intention. And I hope that you were able to recognize and integrate a lot of knowledge from different sort of piecemeal classes that you have taken during the curriculum. Classes on systems, on signals, circuits, electronics, both on the analysis as well as on the design side. So I hope that it was a good experience for you. I hope that it was enriching from an electronics or electrical engineering perspective. If you liked it, you can be sure that you like electrical engineering and you picked the right career. If you didn't like the course, that doesn't mean that you don't like electrical engineering, but there are other things that you can do within electrical engineering. This was more about circuit design, analog circuit design specifically. But overall, I hope that you enjoyed it. I certainly did enjoy teaching the course. Okay, so without further ado, we're going to start the presentations, and I'm going to call on the first team of Michael Shore to present. So I think this is Michael and Jack. So whoever is going to, and it's better if only one a student in the team handles the presentation, the actual going through the slides. Of course, that both can talk and present as you see fit. But so anyway, whoever is going to handle the slides from that team, please share your screen and start your presentation.
So just the problem statement, you guys are all familiar with this. We have an input of pulse train from -5 to 0. So we have to make 2 LT splice circuits. One is going to output corresponding to the input frequency, and one is outputting depending on the pulse width. So the input frequency varies from 90 hertz to 9 kilohertz, and the varying pulse width varies from 80 microseconds to 8 milliseconds. We have a single 15-volt supply to use, and the source impedance of that pulse train is 40 kilo ohms. So these are the test parameters that we had. You guys are all familiar with it. So this is what will be put into that the input pulse voltage source, and these are the expected outputs that we're supposed to get on the graph of the output.
That I did for the frequency to DC. And so on the top left is the input waveform for case 1. So this is at 90 hertz. On the bottom left, we have the input, which it's a network I marked as square, going into a amplifier, which acts as not only as an amplifier but a buffer amp to make sure that the 40K parasitic resistance doesn't affect our output. After that, we have a high pass filter, which acts as a differentiator, and I set the cutoff frequency for that to be twice the highest frequency. So I picked 18,000, and I chose 1 nanofarad for the capacitor value, and I solved for the resistor value to be 8.8 kilo ohms. And then it goes into this one-shot circuit. And then on the top right is the output of the one-shot circuit, which only has negative pulses because the ground terminal, so the positive voltage terminal on the op amp for the one shot is grounded, so therefore anything above 0 volts gets saturated. And this is a 6-order Butterworth filter, which is just 3 second-order active low passes. And that's the equation for a single second-order active low pass. So I assume that R1 and R2 are equal to each other, and C1 and C2 are equal to each other. And I chose the capacitor value to be 1 micro, and I made my cutoff frequency 45 hertz, which is half of 90 hertz, which is the lowest frequency. And that's how I solved for the resistor values to be 3,500 ohms. And when you filter the negative pulse train through this filter, you get a DC voltage. However, the DC voltage is very low, so it needs to be amplified. So what I did was I measured the voltage going into the positive terminal for both cases 2 and 3, and I calculated what gain I would need to get 7.94, well, negative 7.94 and negative 404 volts, and I needed a gain of 11 and 11.36, and the average of that was 11.18. So that's why I chose my feedback resistor to be 10.18 kilo ohms. And this is an offset circuit because the filter introduces an DC offset of about negative 48.8 millivolts. So I needed to offset that. So I have a voltage 80J, which is equal to negative 48.86 millivolts, and that's created by this voltage divider, where V minus is our negative 15 volt supply. And this gives us voltage of 7.79 microvolts when time is less than 1.2 seconds and when time is equal to 3.6 seconds. So that's very close to 0. And so this is the results for case 1. So at 2.2 seconds, we got negative 82 millivolts. The ideal was negative 81 volts, and the average was negative 81.52 because there's a ripple. So that was only a percent error of 0.642% and a ripple of 3.091%. For case 2, there was almost no ripple, and it was kind of hard to calculate, so I wasn't able to. But for our voltage, we got negative 4.05 volts about, and for an error of 0.248%. And then for case 3, we got a voltage of negative 7.77 volts, or an error of 2.141%.
So this is the full schematic of the pulse width DC graph. Schematic. So these are the 3 power inputs. I just like the last one, there's a 40K ohm input resistance, and I labeled the nets so that it will look cleaner in the whole schematic. So this is, so just like Jack did before, I put the input into a buffer amp to clean up the impedance and current issues and get rid of that parasitic resistance. Then it's going into a voltage divider as well, also acts as a level shifter. So what it does is it's taking the square wave input, and instead of from 0 to 5, it's bringing it from 0 to 0 to -5, brings it to 0 to -3.75. And then it brings that 15 volt input down to a 3.75. And when they add, it shifts the entire graph up, the entire square wave up. So it goes from 0 to positive 3.75. So the blue one is the input, and then the green is the output coming to the right. So the reason for this is because when it goes into this integrator, it making it positive is easy to work with, and it's not changing the pulse width at all, because that's really what this is supposed to do. So that output is then feeding into this NMOS. So the reason we picked this transistor is because it has low current consumption and a negligible resistance, such as the ideal parts that we found. So we used with this one. So the way this integrator works is when the voltage is equal to 0, that's the pulse width. That's when it's integrating. So it's generating a triangle wave from this input. And the capacitor used is actually what determines the magnitude of how high this is. So it's scaling the integration. So this was something that we tested with for a while, and I came up with 1.17 microfarads to get as close to this peak value as we can for what the output was supposed to be. And then from that, it goes into this active peak detector. So an active peak detector just includes an op amp, a diode, and the capacitor. So what this circuit does is it finds the highest point, and the capacitance will hold that charge to keep it from dropping. So these C2 and R1 on the schematic, these values were picked so that we can find the trade-off between the ripple and also the discharge time, because the output has to settle to 0 by 3.6 seconds. So if you make those too high, then the output won't settle to 0, but then also the ripple will be too much. So we had to kind of find the balance between the two of those, and 200 nanofarad is what we ran, and then 1 mega ohm resistor, or 1000K as we put in LT splice. And then from here, it's just good practice after an active peak detector to use a buffer amp, and we also put in some smoothing capacitors to remove the noise. We really didn't find any difference, but when we measured before and after this is just for the if we're build a physical circuit, this is just practical for what that would be. So when we tested the 3 cases, this is the first one. We got really no ripple at all. So it was measured at 106 millivolts when it's supposed to be 109, with an error of 2.75%. This is the second case. You can see there's a little bit of ripple. It goes from about 5.19 volts to 4.94 volts, with an average of 5.065, making the error pretty small, like 0.1%, and then the ripple at around 5%. And this is the last case with the biggest ripple at around 5.3%. Max is at 9.72 volts. The min, actually that should be flipped. So it should be the max is at 10.25, the min is at 9.72. And the average of those two is actually 9.99 volts, pretty close to what it should be at 10, with a 0.1% error. These are the references we use for research and designing our circuits. With that, we'd like to open the floor for questions.
I think I saw in the frequency section of the circuit, you use like a -8 volt supply, or you somehow got from the rail to the 8 volt, but why did you need 8 volts instead of 15?
So if you go back to that, Mike, can you go back to the slide with my pulse train?
This one?
Yeah, so the peak of the pulse train on the top right, there the peak's around like -7.2. So I didn't need the entire -15, and so I picked -8 because if anything higher than -8, I wanted to saturate. And I was thinking about removing that, but I didn't really have the time to like debug it because when I changed to the -15, I was getting some bugs that I didn't have time to iron out.
All right, thanks.
Any other questions?
Great. Thank you very much, guys. Thank you.
Thank you.
Thank you.
Now we're going to go to Chuck and Daniel.
Yes. Here, let me. All right, so we're going to start off with a general overview of the project as well. So we were tasked with creating a test equipment that will analyze a pulse train signal and compute the frequency and pulse width as analog output signals. And so the output voltage for the input frequency is going to be defined as V1. For the pulse width is going to be defined as V2. And V1 is going to have a range of about minus 80 millivolts to about minus 8 volts, corresponding to input frequency of 90 hertz to 9 kilohertz. And V2 is going to have a range of 100 millivolts to 10 volts, corresponding to an input pulse width of 80 microseconds to 8 milliseconds. And at higher frequencies, the pulse width range is going to be limited by the equation below. And just some other input signal characteristics. So the initial is going to be at 0 volts, and the V out pulse is going to be minus 5 volts. And the rise and fall times are each going to be less than 10% of the pulse width. The source impedance of the input signal should be less than 50 kilo ohms. In our case, we used 40K. And the source signal can be modulated by a baseband signal of 0.8 hertz. The accuracy, as far as the accuracy goes, V1 and V2 should be better than 10%, but a maximum of 25% is allowed at one point, provided that the average is below 10%. And there's just a general list of all the resources available to students. So section 1 is going to be concerned with the pulse width circuit. So again, we're designing a pulse width circuit that's going to convert the pulse width to a voltage where we're going to integrate over a constant. And so in our design, it consists of 5 main sections. So we have a buffer op amp, a differential op amp, our integrator circuit, a peak detector circuit with a bleeder resistor, and just a series of buffer op amps and voltage dividers, which are going to provide voltage and power to our circuit. So to start off, we had a buffer op amp just to ensure that source impedance wasn't attached to the signal, and just because we didn't want to have any effect on the rest of our circuit design. So again, we introduced the buffer op amp at the beginning of our circuit. After that, the signal is going to go through our differential amplifier, which is just going to create our on-off switching conditions for our N-channel MOSFET, and the op amp is going to be defined by the equation below. And so for our 2 cases where the pulse reaches minus 5 volts, the V out is going to be minus 2.5. And when the pulse width reaches 0 volts, it's going to be plus 2.5 volts. So essentially, we're shifting the signal 2.5 volts in the positive direction. And here's just the output of the differential op amp at 90 hertz frequency and 80 microsecond pulse width. So after that, the signal is going to go through our integrator circuit. And so our op amp integrator is going to integrate over a constant of minus 10 volts, where our N-channel MOSFET is going to determine exactly when our op amp is going to integrate. And so since the MOSFET conducts when the voltage is positive from gate to source, essentially when the pulse hits minus 2.5 volts, the op amp is going to integrate, and it's going to dump whenever the signal is positive at the gate. So the integrator is illustrated by the equation to the left. And when calculating the our theoretical values. We got a value of 8 kilo ohms for our resistor, but after testing with our peak detector circuit, it was determined that we had to change that value. So we got a resistor value of 7,608 ohms, which gave us more favorable results. And again, here's just the output after the integrator circuit at 90 hertz frequency and 8 millisecond pulse width. So after the integrator, the signal is going to go through our modified peak detector, where we have a bleeder resistor connected in parallel with the capacitor. And this is just going to discharge the capacitor at a time frame when the cycle of pulses stops. So we wanted a time as close to 1.2 seconds. So after playing around some values, we got a resistor value of 6.4 kilo ohms. And the output of the peak detector is in the shown in the green waveform. And again, this is simulated at 90 hertz frequency and 8 millisecond pulse width. And to distribute power to our circuit, we have our sources tied in with voltage dividers. And so our integrator circuit required minus 10 volts. So playing around the resistor values, we determined the correct values to achieve minus 10 volts and minus 2.5 volts for our differential amplifier. Here's just some of the results tabulated from the simulation at 90 hertz frequency. And so we achieved values for the V theoretical, our percent ripple and percent error that were all in the within the project specification range. And again, these are our results on a log scale. So we can see the linear relationship that was that we were aiming for from the start. And our results are in the top right, and we compared them to the ideal voltage value versus the pulse width on the left side. And below our results are the theoretical values compared to the pulse width.
So this is the frequency to voltage converter. So the students of Electronics 2 were tasked with designing a frequency to voltage converter, which generates a constant pulse from a one-shot circuit, also known as a monostable multi-vibrator, that would go to a low-pass filter. And for this design, there was a total of 8 main sections, which are the buffer op amp, the operational amplifier comparator, the differentiator circuit, the op amp monostable multi-vibrator, the modified precision rectifier, the ninth order Butterworth filter, and then an inverting op amp that provided gain adjustment and the distribution of power and unity gain buffers. So in our previous circuit, we used a buffer op amp because of the series resistance, which is 40K. So that way there was no effect on the input signal. So I created a comparator basically to get rid of the time rise and time fall, because when the time rise and time fall for our monostable went above 1 millisecond, it seemed to have issues producing a constant pulse. So therefore, to eliminate that, I basically created a comparator where if the V signal was greater than negative 4.95, it would just go to ground. And then if the V signal was less than negative 4.95, it would go directly to negative 5. And then shown here is our output. So notice how the rise time and fall time are basically mitigated, so that way it's almost instant. And this is at 90 hertz and 8 milliseconds. So this is the trigger signal for our operational amplifier monostable. And basically this was decided that it's best when it's 10% of the 5RC time constant. And so I set this equal to 80 microseconds. And then we got our value for the capacitor to be 1.6 nano. And then this is our output for the differentiator circuit at 80 microseconds and 9 kilohertz. So this is kind of what the operational amplifier monostable waveform looks like. The timing period at the bottom is basically going to be the pulse width of the output waveform. And then it goes to the stable state here. So the timing period happens whenever there's a trigger signal going negative. And so basically this operational amplifier monostable is identified by these equations. So the time delay is basically the timing period, and the timing charge is the capacitor charging time. And then, so basically what I did is I set it to the lowest period minus the RC spike duration. And that basically got me this time here. And then basically what I did is I equated this to the amount of time for the operational amplifier monostable. And then it got me this value for the RC. And then I just made it a little bit lower so there was a little bit more time for the capacitor to charge. And then this is our output here. And then we used a modified precision rectifier in order to get the part of the signal we wanted, which was the timing period. So basically what this circuit does is it inverts the signal and then makes the negative part of that 0, basically getting that timing period that we want. And this is the equation for that. And this is our output at 80 microseconds and 900 hertz. And then we had to create a 9th order Butterworth because at the 80 microsecond, 800 microsecond, and 8 millisecond at 90 hertz, at the 90 hertz case, the ripple was very large. So therefore, we had to create this in order to mitigate that. This can be represented by the equations below. So this is solving for the quality factor right here. And then this is the transfer function of the 9th order Butterworth. And so basically I tabulated these quality factors, and then I got the transfer function here, and it also in complex conjugate pair form. And I tabulated the cutoff frequency. I just made it around 80 hertz. And then the gain is shown right here for the circuit. And this is our output waveform for 80 microseconds and 9 kilohertz pulse width. And then lastly, we use an inverting operational amplifier to scale up the voltages and range to make them negative, and also to meet the range margin that we desired. And this is our output at 80 microseconds pulse width and 90 hertz. This is our power distribution here. So basically for our VCC and our negative VCC, we had 8 volts and negative 8 volts respectively for the monostable. And then this is the voltage dividers for our comparator. And this is our tabulated results. All the percent errors for the V ideal and the V theoretical were in range. And our V ripple met all the results requested. And this is our graphs on a log scale. So the linear trend represents that they all kind of match pretty much. In conclusion, both these circuits were sufficiently providing minor errors on both ends. Some of the minor errors can be attributed to the precision of resistor and capacitor values, the reactance of the capacitors used, and or the distribution of DC voltage to the operational amplifiers. For the pulse width circuit, we received an average of 0.799% for the ideal voltage and 0.303% for the theoretical, and all our ripple values were in margin. And then for the frequency to voltage converter, the group received an average error of negative 0.0104% for the ideal voltage and negative 0.420% for our theoretical, and all our ripple values were in margin. Any questions?
Thank you very much, Chuck and Daniel. Very good. Thank you.
Thank you.
Next, we're going to have Alex Ragnar present.
All right, give me a second. And realize this was actually my number. All right, so I was just by myself for this, and I didn't do a I should say I did pulse width, and I'm not going to go over like all the specs for the project. I'm just saying. All right, so for the first part, I just did some rough research on basically what everybody else has been talking about at the start. I just looked into the integration. I wanted to make sort of like a ramp circuit. Well, not ramp circuit. I wanted to make the ramp output and then switch it using obviously a transistor. So basically, I just went off of this information and calculated for 5 volts in and 10 volts out, and for 8 milliseconds for the largest value. And for that, I used also a 40K resistor for the series resistance, and capacitance came out to be about 200 nanofarads. And for the switch, the ideal was to use like a resistor to be connected in shunt with like the capacitor of the integrator, so that during the pulse time, the PMOS will be off. And it would also contribute a very high impedance and completely nullify pretty much the possible DC offset. All right, and for the analog portion, I use a peak detector, like most others. This one's a precision peak detector. I modified it a bit just because I didn't really need the second op amp. I didn't really have much buffering between the load and capacitor. And I just did most of the value. I found most of the values by testing. And just to explain it, the pulse duration, the diodes be on, energy is transferred to the capacitor for this time, and then capacitor is going to be charged the available peak of the input. So here's my circuit. Just a little clarification because I didn't have time. I left in a base resistor. It didn't really need it. It doesn't affect anything if I take it out. So that connection is null and void. And I just have a low pass filter in between to remove frequency spikes. Okay. So I didn't get the value at pulse of 80 microseconds. This is mainly due to the period. Whenever it reaches a certain point, you'll see in the next slide or so, it'll just spike. And like basically the charge, it can't handle that speed. I'll explain the next slide. Precision and error were good for the other two, as well as precision for the 80 microseconds pulse. All right, so for the first one above, you see the 80 microseconds. It just spikes to 9, and the other ones meet within their expected ranges. And like I said before, precision is pretty good, except for, well, actually, no, ripple is good. My bad. Percent error just spikes around a little under 800 microseconds. And I'll show you the tabulated results in a second. You can see that pretty much here. Yeah, it just spikes around 800 and just shoots up. All right, just some notes. It performs well until the period becomes too small, like I said, in pulse width. And adjustment to the period, the circuit, like pretty much just can meet the specs. Ripple is never greater than 10%, so that's fine. And like I said before, the error starts to go above that, running 100 microseconds. And in conclusion, given that it performed correctly for cases with longer periods, it most likely can be assumed that like the DC offset was a problem, which is why I recommended the shunt resistor earlier. And so the pulse and period were much smaller. The circuit acted like the ramp I initially calculated, so it wasn't properly spec'd. And like I said, the shunt resistor, and also provide a constant voltage input into the op amp, about 10 volts, and adjust component values to achieve a better result. And that's pretty much it. Any questions? Probably a fair bit.
Were you able to come up with the reason for why it's such a high output at such low?
Yeah, I kind of touched on it. Basically, since I'm only doing one, I wasn't really thinking about the period earlier on. So I only calculated really for the pulse width. And until later, I realized when the specs were put out that the period needed to be that. So it's like, let me go back to the circuit actually. Yeah. So pretty much it's the DC offset. Like I said, like I would rather like shunt the resistor across this so that I can eliminate that, because when the pulse actually turns on, because that's the input right now, it just like shoots up the ramp. But when I have it in a smaller pulse and period, it's fast enough to counter that.
Okay.
It's pretty much the explanation. So like I said, I was shunted, and also base resistor, like I said, it doesn't really do anything.
Mm-hmm. Okay, thank you.
Any other questions?
Thank you very much, Alex.
Okay.
So next, we're going to have Hussein and Ryan present.
Oh, okay.
Yeah, so we're just going to talk about the two circuits that we implemented for both frequency measuring and pulse width measuring. We'll show our LT Spice circuit and results. So going through first real quick, we're just going to talk about the input specs. We were expected to measure a pulse train that could go from 90 hertz to 9 kilohertz, and the expected values would be negative 8 millivolts to 8 volts respectively. And in our second circuit, we were expected to measure pulse width with an 80 microseconds to 8 milliseconds range. We were expected to assume a 50 kilo ohm source impedance, and we were allowed to use a plus or minus 15 volt supply voltage.
So this is kind of our solution that we created for the frequency circuit. So first it would go, our input would go into a buffer op amp to remove any source impedance on the rest of our circuit. We would use an RC differentiator to kind of use as a peak detector. We modified it slightly to be more of a negative edge detector than anything else. Then we went into a monostable op amp, which would create a constant pulse width output. So it would only be dependent on frequency. We then use another buffer op amp just to separate our monostable circuit from the rest of our circuit. The precision rectifier we use just to get the input pulse train to the correct voltage values so we can measure it more easily. Inverting op amp, and then a Butterworth filter to get the DC values. So this is just going more in depth now. So first we have the buffer op amp. So this has extremely high input impedance and extremely low output impedance. So any source impedance would have no effect on our circuit. For this, we chose to use the OPA 140. We chose this one because it has a dual supply operation of up to 18 volts. So this meant that we could use the 15 volt supply. And this op amp was just really good. So we used it for basically all the applications that required an op amp in both of our circuits. So here is our RC differentiator. You can see that the blue is our input and the green is our output. So we get a nice good peak for the negative edge, and for the positive edge, we have a small little peak, which we kind of can ignore because our monostable only is dependent on the negative edge trigger. Here is just some of the calculation that we did, and we made sure that the RC was less than 10% of the period. For period, we chose the 9 kilohertz because that would be the smallest period. Here's the monostable. So you can kind of see how this works here, with the green being the input from the RC differentiator and the red being the output. When the voltage goes negative, that's when it's actually stable. So you can see that it's stable when the RC differentiator actually goes negative, and we get the nice constant pulse width then. So we had to do a lot of different calculations for this. We wanted to make sure that the time between triggers was less than 9 kilohertz, just to make sure that we can get every single input from the input signal. Additionally, we chose the delay of, that's when the stable signal would be stable. We chose that to be 0.06 milliseconds, and we chose that just because if you have a 15 volt supply output and 0.6, it really gets you the output that we needed. So we're kind of thinking in advance with that. We got the feedback fraction, the timing period, and the capacitor charging. They were just all making sure that we fit within the time between trigger delay. So the output of the monostable op amp was this. So we'd have 15 volts supply when it's unstable and negative 15 when it's stable. And it would be stable for 0.06 milliseconds. Next is just the precision rectifier. So you see The red would be the output from the monostable op amp, and the green would be the output of the precision rectifier. So it inverts the signal, and additionally, it grounds anything from the anything that the input signal will be above 0. So this let us get a 0 to 15 volt supply, as you can see in this equation. So it makes it easier to calculate the average power. So next we need to invert it, just because the specifications for the frequency circuit was to be a negative voltage out. So we had to convert this, so we get a we went with unity just to keep the 15 volt supply. So then we would get 0 to negative 15 volts for output. And then the last part was using a first order active low pass Butterworth filter. So this was used to remove all the AC components and just get the DC value. And then we calculated the cutoff frequency to be about 9 hertz. Though it actually came out to be around 8.8 when we chose our values actually. And we went with unity gain. So as you can see, the gain out would be 1 plus RF over R1. So we just chose RF to be really small and R1 to be really large. So that way it's approximately 1. And then if we just use the average value of a pulse wave, where we have D would be the duty cycle, so that'd be the time stable over the period of the input. And then VP1 would be our V out from the inverting. So that'd be from 0, negative 15. We get this end equation right here. So this was how we related our frequency to our voltage out. And this is just the overall image of how everything was combined together. So this is just a few of the different test simulations we did. So we did 90 hertz at 0.08 microseconds or milliseconds. Here you can see that the average is about 75, negative 75, with a fairly small ripple. There's the ripple, so it's only a few millivolts. Next we did 900. Once again, our values are expected, and we only have a few millivolts here as well. And then this is at 9 kilohertz, and there's the ripple as well. So we also tried plotting them against each other. So we did 90 hertz at multiple pulse widths, because ideally these values should be the same since we're only measuring frequency. And over here, you can see on the left is just all the different test data that we did. And on the right was that 90 with different pulse widths. So we did have one test case go over the 10% error, and that was when we tested 90 with 8 microsecond pulse width. That went to a 12.5% error. But that was the only case that we tested that had that error. We tested the 110 hertz with the 8 milliseconds pulse width, and we didn't receive that error again. So this was just one outlier and everything. Our average error is about 4.5%, and our average ripple was about 0.61%. So we were well within the average specifications. We just had the one max that peaked out. And then here's just plotting the desired in the blue, and then the orange is our simulated. You can also see our correlation factor is 0.9999, which is approximately 1. So our values were very related to one another.
So now we're going to go into the pulse width circuit that we designed and implemented. So the first part of this is our buffer op amps. These kind of remove any effect that the source impedance would have on the rest of the circuit. And then we take a DC voltage that we step down from the original power supply, and our summing op amp sort of acts like a comparator. This generates the control signal for the PMOS transistor that we use to integrate the original input signal. We then invert that signal again using the inverting op amp so that we have a positive signal. And then we hold that peak value using the peak detector circuit that we created. And I'll explain each of these modules individually in the following slides. So as before, we use a buffer op amp due to its extremely high input impedance, and this just prevented any source impedance affecting the rest of our circuit. So we took the input signal and used a DC signal that we stepped down from our power supply. So we wanted to have an output range of negative 2.5 to 2.5 volts. And this would be in the range that we could use to control the PMOS transistor on the next slide. you can kind of see in the previous slide, go back one. Yeah, you can kind of see the inputs to the op amp as the red and green signals, and the output would be our blue. So for our, go to the next slide. Yeah. So for the PMOS switch, we wanted to have it open when the inputs and when the VGS signal is greater than 0.5 and short when it's less than 0.5. And when we have our inputs, when we have this signal from the previous circuit as negative 2.5 to 2.5, that would guarantee that it would always meet those ranges. So this is the integrator op amp part where we sort of integrate the input signal over, sorry. So when the input is positive, we want it to be, the circuit to be open so that it actually integrates. But when the signal drops, it'll close. So we're only measuring the positive part of the input signal. And we made it so that it resets once the switch is closed. So this is sort of some of the math we did to solve for some of the circuit values. We used the steady state equations for when the input is 10 volts and at the 8 milliseconds is when the output should be 10 volts as well. So we use that to derive our resistor values. And this was our peak detector circuit that holds the maximum value of the output from the integrator stage. And then this is what we use for our actual outputs of the circuit. So when we measure the outputs of the frequency circuit, we're using this circuit component. One issue we were running into with the peak detector is that the outputs wouldn't reset to 0 after every peak that we measured. So we added a bleeder resistor to help the peak detector reset to 0. We solved for this using the steady state conditions as before, and we solved for a resistor value of 12 kilo ohms. And this was sort of the function that we wanted our circuit to emulate, in that we measure the pulse width divided by the maximum possible pulse width and multiplied by 10. So this is how we computed our expected values of the circuit. As you can see here, this is our full design synthesis. We implemented this using the OPA 140 op amps, and we simulated this for each possible input signal range. So here you can see our simulation for 90 hertz at 0.08 milliseconds. It followed the expected value pretty well. And on the next is our ripple, which was also followed in spec range. We did it again for 0.8 milliseconds, and the ripple is on the next slide. And this was for 8 milliseconds, so again, followed the expected range pretty well. And this was our ripple. In this slide, we kind of juxtaposed a bunch of different frequency signals together, and as you can see, it's pretty agnostic of the frequency of the input signal, which was expected of our design. And for our results, we had an average error of about 2.6%. Our max error was about 4.8, which matched the spec range pretty well. Our average ripple error was about 10.3%, and our max ripple was 16.3%. And the max difference between our expected and our max difference between the different points on the graph was about -9%. And this is a plot of our simulated data versus our expected. And as you can see, it fit to the expected pretty well.
So it's just a small conclusion. So both of our circuits worked as intended. We were able to get the output range that we desired, and we were able to get a nice DC value out for most cases. Additionally, all of our ripples were below 20%. Our average was also very low for both circuits. Our error was below 10% for the average error was below 10% for both of the circuits, and we only had one case that went above 10% at only 12.5. And anyone have any questions or?
Thank you very much, guys. Thank you. Okay, next we're going to go to Emily and Joe.
morning.
Good afternoon.
Good afternoon. So we're going to be covering our frequency and pulse width detecting circuit design and simulation. So starting off with our frequency dependent voltage
Okay.
source.
Can you share your screen?
Your screen, Abby.
Oh, sorry about that. Can you guys all see?
Yep.
Fantastic. So starting off with our frequency dependent voltage source, we're going to be taking a look at the left side of the circuit. So you'll see we have a flyback diode. So that's going to allow us to power our PNP with a transistor without the capacitor discharge affecting our gate voltage. And when that capacitor, C1, is charged to full, that's going to be on pull down. So on pull up, C1 will discharge into C2. That's going to change based on the frequency of our input. So as, pardon me, the voltage across C2 is going to change with each new pulse. So we made sure that our waveform is going to be able to discharge between each pulse so that we can have a variable input and be able to keep up with it. So it's not going to be zero hold. Our RC tank is going to be controlling the pulse width of our one-shot circuit. So that's also going to low pass with this amplifier here. That's going to make sure that our ripple is really small. All of our ripples were within about a third of the required range. And then we're going to end up with this final amplification here. And that's about a 3.3 volt per volt amplification.
A couple small things to note in the circuit. Can we go back really quick? So there's two time constants that we needed to calculate for, both of which are using R1, but the first time constant is R1C1 and the second is R1C2. The first time constant we set to have according to the maximum frequency, which would mean the minimal period, so that the first capacitor can completely charge up the entire pulse at the input without missing any of the pulses that are occurring. And then the second capacitor needed to be significantly larger so that it would be able to store several of those incoming pulses over the duration. So the idea, the reason why C1 is several orders of magnitude smaller than C2 is so that it's essentially storing up that charge coming from C1.
Okay, and on the right, you're going to see our outputs. So with the first pulse, we don't have the input shown on this graph just because the scale of the output would have been a little bit too small to detect. So that's why you just see blue on the top. And then for the other two, green is our input and blue is our output. They're all going to return to 0 volts within 2.4 to 3.2 seconds. So they're all within our time constraint. Our output error is 6.9 for the first one, percent for the first pulse, and about 2.5% for the other two. And again, all of our ripples are very small.
Okay, so now for our pulse width dependent voltage source. This is just the general schematic of the entire thing. I'm going to go into individual components. A couple things we had to keep in mind is we needed a single power supply, 15 volts. So on the left side, you can see the voltage dividers for the different voltages that we'll be using throughout the circuit. Yeah, can we go to the next slide? Okay, so the first thing that we're doing here is we're on the left side, we're essentially shifting our voltage input up from a range of 0 to -5 volts to a range of 2.5 to -2.5 volts. That's at the output of the third op amp that you see there. That's fed into the gate of a PMOS. And what we're doing here is our integration dump. So we have an input voltage coming at the V10 input. We are scaling that in a way so our input is integrating our PMOS gate is integrating only the higher voltage coming from our V10 input. And then every time that value goes, the 2.5 volt input goes low, it'll dump the capacitor value C1 and discharge out to the next stage. Okay, so immediately after that, we have a non-inverting op amp. First, I'll explain what that's doing when we're looking at the graphs. But the idea is, one, it's acting as a buffer, and two, it's inverting the voltages. And then we have our peak detector. This is a standard peak detector setup. We have a bleeder resistor included in there just so that our output would drop back down to the actual value. And the tank inside of the peak detector is what's determining our time constant for how fast it's going to drop down. Okay, so some of our outputs. Our output error for the third one, I think, is the first thing I want to note. This is the reason why we had a non-inverting op amp with a gain value. Some of our values were significantly far off, like more so than intended. And the smaller the frequency, the output would actually end up on the higher end of what we expected, where the larger the frequency, the output would end up on the smaller end of what we expected. I suspect that a lot of this is due to the capacitor value that we chose in accordance with the resistor in our integrator and dump. But yeah, you can see that these are the outputs that we got. Our ripple is relatively small.
So we'd like to talk about potential improvements with buffer and inverting amp. Those can be neglected, but we would be sacrificing the accuracy, and also we can change the low pass filter, but our ripples, which were well within range, grew very quickly. So we wanted to make sure that we would be consistently achieving the same accuracy throughout any frequency within the range that we were given, and not just those specific pulses. Our settling time can also be reduced with our tank, but again, those resistor values are going to affect the ripples and the output offset. And with our pulse width, we can reduce the op amps, and there's going to be a pretty small trade-off on precision with that reduction of op amps. We also were considering adding buffers so that we could amplify further, as well as the ripple can increase since we're, well within that range. Any questions?
Thank you very much, Amy and Joe.
Thank you.
Okay, now we're going to go to Nick and Ryan.
All right. Figure this out. Good?
Yep, I can see it.
Yep.
Okay, so I'm Nick.
I'm Ryan.
And this is our Electronics 2 term project. Go ahead.
All right.
So to get things started out, we're going to have a table of contents here. So first we're going to start with an introduction, problem description, and the F's and PWs stand for frequency and pulse width, obviously. And we're going to go through each of the deliverables that was required of us and keep going. Go ahead, Ryan. Okay, so for the introduction, the students are tasked with applying the skills and knowledge they have been accruing over the course of their student careers. This term project served to test and evaluate their performance when given a problem that would require the use of both their engineering design skills and also their creativity. Next. For the problem description, this project was designed to test the student's ability to design a piece of test equipment that would analyze a repetitive pulse train input and compute both the frequency and pulse width as output signals. The design was initially supposed to include both a simulation and hardware phase, but this changed due to unforeseen circumstances, a national crisis. The project is currently only based on simulation data, and thus certain requirements of the project may have changed from the term project report requirements and deliverables section. So I'm going to start out with the frequency part. So for the design of the frequency circuit, a total of 7 op amps were used to realize the design. The frequency design, as specified in the requirements document, only utilized at most 2 power supplies of plus or minus 15 volts, 1 signal input, and it only employs the use of op amps, diodes, transistors, resistors, capacitors, and simple logic gates. The design presented in this report meets all the requirements listed above and will be discussed in further detail later on in the actual PowerPoint. And the data collection methods used to test the effectiveness of the circuit were the output expectations given in the qualifications test document. Next slide. So this is the actual circuit, and the design of the frequency circuit is broken down into 6 stages. These are the output labels after each section. The first stage of the design was the impedance match unity gain stage. This stage is responsible for isolating the circuit from being affected by any input impedances like the 40 kilo ohm series resistance of the source that would alter the actual results of the circuit and the accuracy of the design. The second stage was the differentiator circuit stage using an op amp. This stage is responsible for performing the actual mathematical function of differentiation, which in our case, when you input a square-like pulse in nature, it outputs a spike. When you ground the positive terminal, it saturates at positive, so it will never go above 0, so it'll be negative. And the reason why I chose this type of circuit is because at low frequencies, the reactance of the capacitor at the input is very high, which results in a low gain, which then result in a low voltage being output from the actual circuit. And then at high frequencies, I found that it became unstable in its current setup, which only would have that feedback resistor. So I did some more research on it and found that if you add a capacitor in the feedback loop across the resistor, you could prevent that unstable behavior, because when it was unstable, the voltage gain of a high frequency input would be much higher than what I would expect on the values that I chose. So when you add a very small value capacitor, as you can see, it's a 0.01 microfarad capacitor, it completely removes that behavior. And then the third stage was a gain amplifier. This was just to boost the signal because there's going to be losses associated across each of these components. So I wanted to make sure it was nice and high so that I could do my proper adjustments. The V gain of this amplifier was around 3, because you can see there's the 2K and the 1K, and it's a non-inverting. So we all know the V gain is 1 plus R, in my case, R4 and R over R3, which is 1 plus 2K over 1K. So there you go, 3. And then the fourth stage of the design was the signal inverter that basically just flips it into the negative part. And that was done through, I believe, R6 is the input. Then the fifth stage was my filtering stage. I decided to use a Sallen key filter, which is essentially similar to a Butterworth, but there's some minor things that are different there. I actually used a specific op amp, an LT1886, which is a high precision operational amplifier, instead of using a generalized universal one. The filter is responsible, obviously, for filtering the signal, but I chose my cutoff frequency to be a lot lower than maybe some other groups have chosen. I chose it to be around 8 hertz, because I used the equation 1 over 2 pi RC, which is 1 over 2 pi times 1.75 kilo ohms times 12 microfarad. I could have used a higher, lower value of that, but the ripple was already non-existent after that point, so I didn't really choose to go any farther than that. After that stage, I did another gain amplifier to boost it again. The ratio there is a 19.5 to 1, but you add 1 to that, so you get a 20.5 factor. I adjusted that gain based on what I needed, because I wanted to keep my offset as small as possible, because I wanted to keep my end voltage when it's beyond the actual testing phase as close to 0 as possible. So after the gain amplifier, we have the final stage of the circuit, which is my variable gain offset adjustment circuit. Basically, has a gain, an amplifier gain, and then I use 3 voltage dividers to get the proper voltage to keep me within the actual 10% specification. Okay, next slide. These are the equations that I use for the differential amplifier, the Sallen key filter, the voltage divider, general equation, non-inverting amplifier, and then an inverting amplifier. Next slide. So this is the input for the 90.9 hertz input. Next one. That's the output. As you can see, the value at the output is negative 75 millivolts within 10%. Next one. And that's the ripple. The ripple there was around, I believe, 1.8 millivolts. Next one. That's the input for the, excuse me, the 4,500 hertz signal. And then the output there is around negative 3.8 volts within 10%. Next one, that's the ripple. As you can see, it's very small. When I zoomed in on it, it got even flatter. So keep going, there we go. And then that is the input for the 9 kilohertz signal. The output, negative 7.499, so about negative 7.5 within 10%. And then that was the ripple, same deal. Okay. And then this was the data analysis. So this was during the qualifications test. These measurements were, we would present it with a test signal. Test signal went in, and then we measured at those around 2 seconds was when we were supposed to do, 2.2 seconds, I believe. And these are the values I got, along with the respective errors, all within 10%. And the only one I could find that really had a substantial ripple that wasn't in the order of microvolts was for the first signal, which was at the 90 hertz. And I met all of the ripple requirements, which is less than 20%. Next slide. So this is the test data graph based on a log scale plot. This was done with the data that will be seen on the next slide. So then this is the 3 different sets of data for different frequencies along those decades. Next slide.
All right,
Okay.
so this is the solution presentation for the pulse width circuit. Again, these are the materials we used, 7 op amps. We were only given 2 power supplies of plus or minus 15 volts, 1 signal input, and I'll go over the output expectations and the circuit construction. So right here is the input signal, and we used unity gain buffers for that, and that goes into a summing op amp where it was added against 2.5 voltage from this voltage divider over here to offset the voltage from negative 2.5 to positive 2.5. And a gain was applied here of 2 to get the voltage from negative 5 to positive 5. And this summing amplifier output went into our MOSFET or PMOS. So I guess it was the same thing. What this would do is when the voltage was below 0, it would reset this capacitor, discharge it. But when it was above 0, it was high, it would give it time to charge the capacitor. And the input of our op-amp integrator circuit was positive 10 volts. Again, another voltage divider. And this capacitor value was found by using the general equation that it takes approximately 5 RC time constants to fully charge a capacitor. So with that in mind, I already knew what the resistance would be. Well, the series resistance would be from this resistor. So it was just multiplying 5 by our fastest case or smallest one, which was 80 microseconds. And I got the value around 4.5 microfarads. Next off is the inverting op amp, which is used to invert the output of the integrator to make the peaks positive for the peak detector. And here I would apply a gain appropriately to match the peaks for the lower end and the higher end for the test signals for whichever applied. So I would mainly concerned with plugging in these 2 cases, the 80 microseconds and the 8 milliseconds, and I would apply the appropriate gain to see how far they were off from, it was the 110 millivolts and 10 volts. So I just found a gain factor that would work for both of them when finding resistance values. And next, I just used a classic peak detector circuit setup, and I saw a lot of groups use the bleeder resistor. I didn't consider that. Instead, what I did is I just changed the capacitance. I made it higher, and that discharged the output faster. And you'll be able to see that in the next slides. And these are the design equations. Whoops. So this is the gain equation, the summing amplifier gain, summing amplifier circuit used, the topology used for the integrator circuit with the reset, and the inverting op amp gain. Next is the simulation results. This is the first test case. This is our input signal. And this is the output signal. And this is the ripple. This case had the most ripple, and that came because when I changed the capacity into the peak detector, the ripple also increased, but that was to sacrifice it for it to discharge better to fit our requirements. This is the second test signal. Again, we have the input, the output. There's less ripple, the lower the frequency goes. I mean, the pulse width, same thing, but ripples. And next is our last case, and the ripples are much smaller. Input, output, and the ripple again. And this is our test data analysis. These are the outputs I got for my circuit. I was off, the most error I got was 92%, but
0.92.
that's 0.92, yeah, my bad. 0.92%, and that's from the first case, which had the most ripple. And we were within the ripple requirements and precision. And this is the test data that was taken to make this graph, which shows as the frequency increases, the voltage decreases for our circuit. I mean voltage, yeah. Whoops, that's a typo. But this is the log plot. And these are references for frequency and for pulse width as well.
Yep.
So any questions?
Thank you, Nick and Ryan.
Thank you.
Thanks.
And now, last but not least, Blake and Joelle.
Awesome.
What's the hotkey for presenting again? F12? No. Shit.
Is it
What's the-
F5?
the bar's blocking it. Yeah.
F5?
Yeah, thanks.
Gotcha.
All right, so this is our project. I'm Joelle.
Blake.
Awesome.
Just to go through, I mean, we're gonna probably fly through some of the stuff in the beginning, just because everyone has already heard it. But so this is our agenda. We're gonna go through the problem statement, solution presentations, design equations, synthesis, simulation, test data, and then finally some conclusions. So the problem statement is that in order to test a repetitive pulse train signal, we need a circuit to compute the frequency and pulse width as two distinct analog output signals. Now, this is the input waveform, everyone knows, and we should also note that it is bound by that equation at the bottom as the frequency increases, the pulse width. And these are the key output characteristics we're looking for. So for the two channels, as I called them, for pulse width and frequency. And so this is the solution presentation.
All right, so I'm going to start with the frequency subcircuit. So starting off is going to be the monostable multivibrator, and the goal is to have the input signal so that on every falling edge, we want a constant pulse width so that the more pulse widths we have, obviously, then the average DC component will increase as well. So, and we also want the pulse widths to be short enough so that it catches from 90 hertz to 9 kilohertz. And that'll be discussed later on. So this is the topology that was chosen. It includes a differentiator at the point, at the input, so that, and then with the diode to clip the positive triggers so that only negative triggers are feeding into the positive terminal. And then it'll switch between two states of an unstable and stable state.
And yeah, and the last thing is that so the pulse width that we choose directly impacts the voltage output, is what we're saying. So essentially, if you have the same number of pulses, but one pulse is 2 times as long, and that pulse is at negative 15 volts, it's going to directly change what that output voltage that we get is. So we need to consider that.
Next is the Butterworth low pass filter. So when it comes to filtering, if you had a standard, 2-stage cascade RC filter, the Q factor would only reach to 0.5. So if we want the Butterworth, filter, we need to have a Q factor of 0.707 to be exact, which has that relatively flat passband response, but then tails off at the end. So, and then ultimately that filter will extract the DC component from the triggers. And in order to increase the Q factor, we need some sort of positive feedback. And that's why the Salem key topology was chosen. And it also includes some gain to increase the Q factor. And then in the end, this is our chosen topology with a buffer at the input, followed by the differentiator, the monostable multivibrator, then going into the Butterworth low-pass filter, and then wrapping it up with another buffer at the end.
For the pulse width circuit, so essentially what we're going to be using to extract the pulse width is an integrator, and we're integrating over a constant supply voltage. And that's going to be the negative supply voltage, so that we get a positive increasing waveform as we see down here. And we don't want that to integrate indefinitely and increase indefinitely, and we need to limit it to the periods that, as determined by the input waveform. So we're going to reset that via an NMOS, like many of the other groups have done. And to get that, we're going to use a DC level shift on that input voltage and shift it from 0 to -5 to now 0 to 5, or 0 to some voltage greater than the threshold voltage of the NMOS. And that's what this topology looks like here. So we're using a simple 3 resistor DC level shift. The NMOS is connected across the integrated capacitor, and the source is tied to the virtual ground of the op amp. And so the next portion of the circuit is just the precision peak detector. And it's going to behave like this waveform shows down below. We're going to be using an op amp superdiode, much more simple design than all the other groups, which might lead to some of the interesting things we saw later on. And notice the bleeder resistor here as well to get a predefined degradation or droop across that this response. And so what the peak detector, the way the superdiode works is essentially it's a voltage follower that's taking the input and driving the op amp, or driving the diode high enough so that the voltage on the other side of the diode is equal exactly to the input. So it's essentially removing the drop across the diode. And this is the final solution, just everything chained together with buffers at the beginning and end. And I would say this buffer at the end is very important as well, because otherwise the capacitor might discharge into the load, and we want to maintain the values.
All right, so these are some of the design equations for the multivibrator, and the minimum pulse width that we could be dealing with is 80 microseconds. So that's why we want those spikes to be under 80 microseconds to catch every single falling edge. We want a beta value, which consists of R5 and R6 on the right side of the circuit. We want beta to be large enough to avoid any sort of misfiring based on the hysteresis curve. And on the left side, you'll see a negative DC offset to really separate the two states so that there's no misfiring like we had originally. And these are some of the design equations in that the DC offset is just simply a voltage divider. And the pulse width is a product of R4 and C2, and then the natural log of 1 plus R6 over R5. So now for the Butterworth low-pass filter. As far as the cutoff frequency, it's just good design practice for it to be about 10 times the baseband frequency. From that, we could easily calculate omega naught is just the cutoff frequency times 2 pi. And then assuming that R1 equals R2 and then C1 equals C2, we can simplify omega naught to being 1 over RC. The Q factor, we want it to be 0.707, and that's it's directly related to the gain factor K. So based on, we could find K based on Q because we have 0.707. And once we find K, we could then find a nice ratio for RA and RB.
For the DC level shift, essentially, it's just a voltage divider. So what we have here is I took the circuit, and we have VDD, which is that supply voltage, and then I have the input coming from the buffer, and it's going to be divided through R4 and R5. And so when the equivalent circuit to this, you can see the equation kind of boxed in here, is VDD minus V buffer. And noted that this DC level shift is not going to be constant, because as the buffer changes, so from whether it's applying the 0 volts or the -5 volts, that divider is like the resistance values are not going to change. So essentially your output is not going to give you a nice clean shift, which is due to the topology, but it does function the way we need it to. So we choose to design so that the input logic high becomes like 0 volt and the logic low becomes greater than the threshold voltage. The integrator, the analysis is really simple, just ideal op amp. If you look at it and you just recognize 1/S as an integrator, you get this design equation down here where V is the constant input reference voltage. And then for the peak detector, this kind of like recap of RC time constants that everyone has kind of mentioned. So the equation for discharging capacitor is seen here as V naught. So that's the voltage of the capacitor at the beginning of discharge. And the time it takes to deplete is given by RC. And I used about 4 RC, just the 98% mark as kind of the benchmark for discharging.
So now solving some of these values. So we chose tau to be, and then this is for the differentiator. So we want it to be really short so that we could get sharp, narrow spikes feeding into the op amp for the multivibrator. So we just chose a standard 20 microseconds and a C of 2 nanofarads, and then we could calculate that R would be 10K. As far as the beta value, we chose another value of 0.6 to keep it high. And then we could find that ratio of R6 being 30K and R5 being 20K. And then for the pulse width, we want it to be under 80 microseconds. So we played around with some values, but we determined that the best performing value was 38 microseconds. And then we chose C2 to be 0.5 nanofarads. And solving the equation down below, we have R4 being 86.58 kiloohms. And then the fourth part down below, bottom right, we wanted the DC offset, the negative DC offset, to be about like a 16th, just definitely below 0 volts. So calculating R3 and R2, we could have a 1K and 15K.
Hey, and a quick note on the 38 microseconds. The way that we got to that number was essentially we took the completed Salem key like Butterworth filter and then fed it like ideal pulses to see what pulse width do we need to give this like our filter to produce the exact like DC voltage levels that we're looking for at the output. So this way we can avoid any amplification or anything like that.
So next for the Butterworth low pass filter, our baseband signal frequency is 0.9 hertz in the specifications. 10 times that is 9 hertz. So that'll be our cutoff frequency. And that relates to an omega naught of around 56 radians per second. So now if we choose an arbitrary value of R equals 15K, we could calculate that the C will be, our capacitor will be 1.7 nanofarads. And then, like I mentioned before, the Q for the Butterworth is 0.707. So that means we could solve for our gain factor K, which is 1.58. And then we have our ratio right there. And so that ratio will be RA equals 5.86K and RB equals 10K. And that K factor needs to be below 3 in order for the system to be stable. And this is the topology like you saw earlier, but with the values attached to it.
For the DC level shift, so I just chose R5 as so let's just start on the right. So if we plug in the values for the buffer and the supply voltage, we have 15 and -5 volts. And now I'm designing for a 0 volt output at V out in this situation. And so what that gives us is that R4 is equal to 3 R5. And so just choosing R5 as 10 kiloohms, we get 30 kiloohms here. And then R5 and R6 is 10 kiloohms. R6 isn't pictured, but it's it'll show you in the SPICE schematic. And that's just to prevent the buffer input from getting tied directly to ground. Now just to verify how this will function in the other case where the buffer is inputting 0 volts down here, we compute this again and we can see that we're going to get an output voltage of 3.75 volts, which is above the threshold for the NMOS that we're using. The integrator, so for this we needed to calculate essentially the slope of the integration. So we know how long we want for like an 8 millisecond pulse. We need the slope to reach 10 volts. And so applying the design equation, we can see that our C time constant is 0.012. And so picking our value, just 10 kilo ohms, we get 1.2 microfarads as our capacitance. For the peak detector, we need to be able to track the base bandwidth changes. So if the peak is decreasing, we need the peak detector to discharge enough or droop enough that it'll be able to catch this decreasing pulse width. But we also need to maintain accuracy in that case that it has to hold the longest hold case it has, which is 90 hertz frequency, 80 microsecond pulse width. And so that gives us this range for values. And then so just picking a capacitance of 20 nanofarads gave us an R value of 8.33 mega ohms. Putting that all together, we get the following circuit. And this is the R6 I was talking about right here, going to ground, it's 10K.
So now just following the signal from the input all the way to the output, this is what our signal looks like and from the input after the buffer. Once it goes through the differentiator and through the diode, we could see that before the diode, we have these spikes here in blue. And then after the diode, we have the negative triggers in red that will feed into the terminal, the positive terminal of the op amp. So at the output of the monostable multivibrator circuit, we have these constant pulses in green, and then that's the input in red. So you can see on the falling edge that will trigger the pulses. And then lastly, at the output of the filter, the red line is our DC component. So this was the second test case, and you can see that we measured very close to -4 volts from the filtered output.
And repeating the same thing for the pulse width. So we have, this is the input after the buffer, which is the exact same thing as the regular input. And then taking that and taking the DC level shift, we can see we go from 0 volt to about 3.7 volts, which matches theoretical expectations. And that produces, so when we're resetting that signal from the integrator and with this slope, we can see that we're reaching 10 volts on each of these and getting a nice clean reset. Applying that to the peak detector, we can see that we are tracking, there's a like pretty decent ripple there, and that we will discuss a little bit later. And then that is the output that taken to the buffer. So the following is like the test data and analysis.
Yeah, sorry. So this is the frequency subcircuit, and the dotted red line is for ideal voltage, that linear graph, and then these are our test points. So very great results that we got, ranging from 0 to -8 volts. This is the same data, but just with a logarithmic scale. And this is output voltage precision and accuracy. So this is the error. The error was under 5% every single time. I think the max, you'll see later, but under 5%. And then the ripple was close to 0, if not is 0 for most of it. The first 3 test cases were in the microvolts as far as ripple, and then it just continued into the nanovolts for ripple. And here we go. So for the average percent error, we had under 5%, 4.4%. For the average percent in ripple, it was about
Can anybody hear me?
Oh.
Is he here?
I lost
where did you?
internet, but it's
What
back.
about the slide you saw?
Do you want us to go back and repeat?
Yeah, go ahead. I think you were talking about the error statistics for the frequency channel. Okay. Yeah, there.
Okay, this was the last thing you heard?
Correct.
Oh, okay. All right, then Blake, you could probably just reset your results from the pulse width side.
Okay, so this is like the same data illustration as Joelle was mentioning, and everything is very linear. So, and then applying the log scale just to help us see sort of at the first decade, kind of more clearly distinguish between the points, because otherwise everything is grouped very closely for that 10 data points per decade testing scheme. And so looking at that, we can see that the first point is the highest error, and after like 368 microseconds, we can see a steady increase in error, which I was going to discuss in the conclusion. But it's not as visible in this plot here simply because of it's a percent error, and these are smaller values. So overall, the average percent error is about 2.5. The percent ripple is about 5, both of which are well within spec. The maximum percent error is actually 9%, and then percent ripple is 6.5. And so just relating those to the specifications, it's at 15% improvement and a 71% improvement respectively. So for the conclusion,
yeah. So for the monostable multivibrator, it doesn't produce constant pulse widths as frequency increases. Therefore, it incorporates any non-linearities.
Yeah. So yeah, the biggest I guess source of error was, and when you got down to like 80 microseconds, essentially we're supposed to be designing for that 38 microsecond pulse width, and it's dropping down to like 30 microseconds, which obviously gives you like a significant DC sort of error, and that's where most of our error was coming from for the frequency side. For pulse width, so I was having a lot of difficulties getting the peak detector op amp to work properly, and this is maybe because of the topology that I used. But basically, whenever the diode is open, the op amp loses its feedback and goes to its negative rail, and it stays at the negative rail, and then it needs to drive from the negative rail all the way back up to the voltage level of the diode in order to charge the capacitor. And so what would happen was at those lower frequencies, it would start to miss pulses and just not react quickly enough to those pulses. And so what I did to counter that is I put one of the rails to ground instead of negative supply voltage. And that added, now the op amp was unable to drive the voltage at the end of the capacitor completely to 0 because it could only go down as far as ground for its output. And sort of that is still an issue that needs a little bit of tweaking for that error at the really small microsecond range. But any questions?
No, thank you very much, Blake and Joelle. All right, so this concludes the presentation. I wanted to reiterate that I hope that you learn a lot through the experience. I think that the group, as a group, perform extremely well, actually very, very well. And I'm very, very proud of you guys, okay? So I know you put a lot of time and effort into it, regardless of the special circumstances. So I guess I will be seeing you guys during the final. That's on the 19th, okay? And before I go, I wanted you guys to meet someone. This is Loki.
Hey.
This is Loki. She was named after Thor Nemesis, okay? Even though she's a girl, but she's really feisty. And say hi, Loki. And it was named by my daughter. So so she lets us live here, okay? It's her house. All right, guys. Have a wonderful end of the semester. I wish you the best on the finals. And again, I will keep office hours normally until the final. So yours is the last final that I have on the 19th. So thank you very much for your attention, for your questions, and wish you the best on everything. And if you ever need anything, reach out. So again, best of luck on the final. Thank you so much, and have a good weekend. Okay.
Thank you.
Thank you.
Thank you so much.
All right. Bye-bye.